Thanks for joining this session. So today that will be quite unusual format for us. We are going to skip most of the theoretical part, as we usually do with our talks, and rather we'll focus on the technical aspects of Apache Ignite. In particular, we are going to build an application using a special schema. And with this schema, we want to complete that application that was created for us initially, but throughout the code of that application, we have a lot of to-dos left. And whenever we would try to start some of the pieces of that application, we are going to get some failures. And the goal of this session is to fix everything. And most of those issues and most of those to-dos, you will face them. You will hit them whenever you will start building your Apache Ignite applications. Speaking about the schema, I'm going to use the world database one. That one is usually available for major relational databases like MySQL or Postgres. And we also have a version of this schema created for Apache Ignite. I'm going to launch and have 2 nodes cluster on my local laptop. And most of the time, throughout this coding session, we are going to work with 2 tables, with the country table that basically stores all the countries of the world, and the cities table that respectively keeps the cities that are located in all those countries. As for the learning curve, what I'm going to show you, like in particular throughout this session. First of all, we are going to start with SQL. That's my kind of personal preference. When it comes to Ignite, there are several ways how you can configure your cluster and your schema. You can use cache configuration, you can use a programmatic approach, but I'm a kind of a relational guy who has a solid background with relational databases. That's why I will start with SQL. And next, once we create our first cluster and define that SQL schema and experiment with SQL queries, I'm going to switch back to the key value APIs. We are going to start our first Java application that uses key value APIs to update records, to update fields, and to read some records back from the cluster and bring it to the application. After that, we will see how to use Ignite distributed transactions if we need to update 2 or more records atomically, cluster-wide. That will be demonstrated with the usage of our cities table. After that, some of the tasks, some logic requires us to process pretty much data, a lot of the records. And instead of bringing this logic from the server side to the application, and I will show you how to create a custom Java tasks, how to avoid common pitfalls with those programmatic approach, and how to run those custom Java tasks on your cluster machines. And more important, how can we update those custom Java tasks on the application end and get the classes of those tasks reloaded automatically for us and brought back to the servers. After that, we will going to finish our session by looking how we can listen to the data changes updates with continuous queries, so the applications can subscribe to data changes that happen on the server side and receive notifications and then act accordingly. And finally, even though Apache Ignite is an in-memory computing platform, it doesn't have a lack of persistence. When you go in production with Apache Ignite, you have a choice of where and how your data will be stored and persisted on disk. And I will go to demonstrate you how to use Ignite native persistence for that task. All right. Throughout this session, I'm going to use a project with source code templates. As I said, the project is left deliberately unfinished for us, and we need to complete it. And it's up to your preference. You probably can follow me, or even better, just watch, follow my steps, and then you can download this project and repeat and build this project at home at your free time. Okay, part 1. So SQL APIs. Right now, we are going to use SQL to create the very first tables, the world database schema for our cluster. We are going to use create table commands. We are going then to use insert commands to populate the table with actual data. And then I will show you how to query data back from the cluster using standard select statements. Okay, let's switch to the terminal window. So what I've done before this talk, I went ahead and downloaded Apache Ignite 2.8.1 release from the website. So I'm using the latest version of Apache Ignite. And right now, let me start my very first Apache Ignite cluster node. While the cluster is being started, I'm using this configuration, and this configuration file is located in this template project that you can go and find in GitHub. No worries, at the end of this session, I will show this reference to the GitHub project once again. If we look at the content of this XML file, we will see that the settings are pretty straightforward. Generally speaking, I'm defining Ignite configuration bin. Inside of this, that's a wrong one. Let me open. That's a configuration of a complete project that has the whole application working, and that's the one I need. So this one defines data storage configuration. So basically, I'm saying that I'm giving every server node no more than 150 megabytes of memory space. Then I want the cluster nodes to report various metrics that I want to observe using management tools. And then by default and right from the get-go, I am enabling the native persistence. All the records that will be stored in memory, they also will be persisted on disk. And that's the most important configuration property, especially for the beginning. Here is I'm defining the networking settings, saying that all my server nodes and my applications should search for each other on the following loopback interface whenever they want to form a cluster or whenever an application wants to connect to the server nodes. All right. And now if I jump back to my terminal window, I can see that this cluster node is started. You want to search for this line in your log output. Actually, we have only one cluster node right now. Let me run the same command on a different tab so that I have a 2 nodes cluster. Okay, the second node is up and running. And right now, what I want to do, I want to check, observe my cluster metrics and manage it using GridGain control center. To do that, I need to copy this unique cluster identifier and paste it into this GridGain control center UI. So actually, I need to add this cluster to the UI. Okay, the cluster is found, but it's not activated. Let me activate it. You need to activate the clusters of Ignite that have Ignite native persistence enabled. For pure in-memory clusters, you don't need to do this. All right, the cluster is up and running. So here is the tool reports validly that I have 2 nodes in my cluster. That's like how much of my Java heap is used. That's how much of off-heap memory I have, and there is nothing in memory yet. I have not created any database yet. And that's like the kind of the storage size, the native persistence metric. That's how much disk space is occupied. So the cluster is ready, but the cluster is empty. So the next step for us would be to load the Vault database schema. And to do that, I'm going to use SQL line tool. This tool is also shipped with Apache Ignite within Apache Ignite distribution. So I just need to execute this command, and I will connect using the JDBC driver of Apache Ignite. All right, I will able to connect to my local cluster, and right now I want to preload this database. Okay, let's start the preloading. And once this happens, let me show you what's inside. That's the script. So generally, the script drops the tables and indexes if they were existed before. Next, it creates the country table, it creates city table, country language table, etc. Basically, quite familiar syntax, and we are using the same ANSI 99 SQL approach to create and define schema in Apache Ignite. Okay, the table is created, and the next step for us would be to double check that we can run the very first SQL queries over it. I'm going to the SQL screen of GridGain Control Center, and here is I can find schemas, public schema, and it's my city table, that's my country table, all the fields are listed, etc., etc. I have already predefined some of the queries, so let me run the very first one. This one queries only the country table, and basically it returns us the most populated countries in the world, the top 3 most populated countries. And it's not surprising that China, India, and the United States are, in fact, the most populated countries. Let's execute a bit more advanced query. This time, I want to join country table with city table. And right now, I want to return the most populated cities among the following countries. So here is we are going to join two tables, we are going to group records, we are going to order records. And when I execute this query, I'm getting some results. So for some reason, Nagasaki, Fujiso, Otsu are reported to be the most populated cities. And in fact, that's not a valid response. That's a wrong result. Why do I see this? If I show you this slide, on this slide, when I was introducing you this sample application, all the records, all the cities that belong to a specific country are located on the same cluster machine. And to achieve this distribution, we need to set up so-called affinity keys. An affinity key helps you to define this relation between a parent entity and a child entity. And we did not do this in our SQL script when we were creating the city tables. That's why right now, when I'm running this query with join, some of the records are distributed, the city records are distributed randomly. That's why when the nodes do the join, they kind of don't have all the records available locally, and that's why the result is wrong. How can we fix it? First of all, you can allow so-called non-collocated joins, and that will enforce data shuffling for the joining phase. When the nodes will join the data, they will reach out each other, kind of transferring over the network missing records, and that will help to produce the result. Or the second approach, we can set up the affinity key to avoid this data shuffling phase. But first of all, let's use this data shuffling. Let's allow non-collocated joins to see a correct result. The correct result would be Seoul, São Paulo, and Shanghai are the most populated cities. And right now, what I want to do, I know this relation, and let me define these affinity keys. To do that, I just need to do one little change in the create table statement of the city. In particular, I need to set that affinity key is country code. What this instruction says, it says that whenever Ignite will be inserting any cities in the cluster, it will be using the value of the country code to determine a target node that has to store a record. And it's not surprising that all the countries that share the same country code will reside on the same cluster node. All right, we've done this improvement. Let's reload the database. It will be really quick. So it takes a little bit more time because we also need to drop some metadata. We need to remove data from the persistence, etc. It's not just the data is being removed from both memory and disk tier. And right now, yes, I no longer need to use non-collocated joins. I know that the data is now collocated. And if I run this query, once again, you can see that, okay, it returns the same result set, and there is no more data shuffling. So actually, we achieved this distribution. By setting this affinity key, right now, all the records that belong to the same country are located on the same machine. And when you do advanced queries, like queries with join, you avoid any data shuffling, and your query will perform much faster. Okay, that was for SQL. Let me quickly check the question tabs. Someone is asking questions. I know that those were references from Wenka. Yeah, guys, anyway, I will be taking pauses. If you have any questions throughout this conversation, don't hesitate to put them in the question tab or in the chat window. I will be checking them before I'm switching from one topic to another. All right, that was SQL. So what we've done, we defined the tables, we inserted records, we created the tables, and we also showed how we can set the affinity keys so that we can run efficient joins or more advanced queries. Next topic, key value APIs. With key value APIs, you have an opportunity to request or update individual or like several records if you know primary keys for your data. Like in here, your application might know the value of key 1, key 2, and then you go ahead and you can get those records from your cluster. And Ignite can easily take and map a particular primary key to your specific cluster node. So what we are going to use next, here is we have this application template available in this project. And what this template does, it connects to the cluster, to my cluster nodes using the client node, thick client of Apache Ignite. Then I'm getting access to the Ignite cache, which is named country. When I was creating the country table, at the same time, it created this abstraction of the cache. So whenever I will be using the caching APIs, I will be using the abstraction of caches. Whenever I'm using the SQL APIs, I'm using tables. But anyway, internally, everything looks like the same. The data is stored similarly. Okay, and then here is I have the get put country method that returns me. I'm trying to get the record of the United States. That's the primary key of the countries. If you check their DDL statement, that's our primary key, the code value, and the code is char, which transforms to string type in Java. I'm getting it, I'm checking who is the head of state, and then I'm updating the head of state to Donald Trump, that's the current president, and then I'm writing back this record. So let me run this query first and see what would be, if there are any errors. We have to get some errors because this application is full of to-dos. And our first error is class not found exception. And if you check with the stack trace, what happens here, it was reported in this line. So generally, when I was able to locate this record with the primary key from the cluster, but when everything failed, when Ignite was trying to deserialize it to the country object. And the problem here is that when I was defining my country and city tables, I did not tell Ignite what other Pojo classes my records should be deserialized to if I want to use those deserialized versions in my application code. And to fix it, here is we have a hint. I need to update my DDL script again and reload my database. So all my data, all my Pojos are located here. I have country Pojo, I have city Pojo, I have city key that I will show you a little bit later. And what we need to do is to update the script once again. So generally, when Ignite would be creating this table, I am telling Ignite that whenever the application wants to transform a record, the raw record to a class, it needs to be transformed to this Pojo instead of this one, something that was kind of randomly generated by Ignite. We don't have this class for sure. And next, let's do the same for the city. We don't use the city table yet, but we will do it a little bit later. So I need to update it here. And also for the city, we are using a complex key. With countries, it's simple. The key is like just one field. With cities, we are using a compound primary key that consists of ID and country code. That's why when we want to access city records using this compound key, we need to create a special Pojo class for the city key. Okay, and now this, if we reload this database again with the new settings, this exception will be resolved. Let's wait. It's reloaded. And now I need to restart this application. All right. Yeah, that exception is gone. That's another one that we would need to fix later. But the very first method worked out well. So we see that the initial president was George W. Bush. That's what was reported by this part of the code. And then I updated this president record to Donald Trump, etc., and brought this record back to the cluster. But then I was trying my logic, my application tried to execute another method. With this method, I'm trying to get the current head of state, the current prime minister of the Great Britain, but then I'm trying to update the head of state, the prime minister of the Great Britain, using entry processor abstraction of Apache Ignite. The difference here is that when I was updating the president of the United States, I was bringing the whole record from the cluster to the application, and then I just updated a single field and brought back this record to the cluster. When I need to update an individual field, instead, I can use this entry processor approach. With entry processor, this logic will be executed on my server nodes, and then on the server nodes, I'm just going to update this record. That's it. But the problem is that this application says that the class of this entry processor is not available on my servers. So servers don't have it in the class path. And we have two possible options. You can compile this class, produce a jar file, and add the jar file to the class path of your server nodes, restart your cluster. I don't want to do that. Or instead, you can enable the peer class loading feature of Apache Ignite. That's what this demo to do suggests us to do. Once you do this, let me do this thing. When I do this, I need to restart my cluster. Usually do this once, and you would do this before you go in production. Let me stop my cluster nodes. So I'm restarting with the peer class loading enabled. I don't need to reload the database because all the data was persisted on disk. So Ignite will, upon the cluster restart, Ignite will read all the records from disk, and nothing is lost. Everything is on disk right now, and will be loaded in memory in background while we are querying the cluster. Okay, the cluster is up and running, and right now, if I restart this application, Ignite again will try to execute, the application will try to execute this logic. This request will arrive to the cluster nodes. The cluster nodes will not find this class in the local class path, but they will transfer the bytecode of this class from this application because the peer class loading feature is enabled. So if you see, I'm no longer getting this exception. So basically, the server nodes read the class, the bytecode of the class over the wire. But right now I have another problem. So this Ignite server node started executing this logic, and it said that right now we don't have the class for the country table, our POJO class. And the problem here is that presently peer class loading has one limitation. It can transfer all the classes from the application to the servers with the peer class loading, unless the POJOs unless the classes for the data you store in your caches. So right now, here is I was trying to get and deserialize the value that is stored in the country cache, but unfortunately, this class cannot be transferred. That's the current limitation. And to work around this, again, you have an option of assembling a jar file with this class and adding it to the server nodes, restarting your cluster, or you can switch to the binary APIs of Ignite that will not require you to restart the cluster all the time. And I will fall back to the binary objects API because that would allow me to read and update data on the servers, not even having access to the POJO classes. So let me do this really quick. I am going to use binary object interface instead of country. We need to use binary object builder. We have entry, get value to builder, and then I'm saying the builder set field head of state, the value of this field to Boris Johnson. After that, I'm telling that we need to update this value, this entry, sorry, builder build, and that's it. And this record will be updated right on the server node with the help of this entry processor. And now let's return get value field. Let's return this current, the new value, the new prime minister record to my application. So this part will be executed on the application. This part will be executed on the server. So there is one little change we need to do in here. We need to tell that Ignite API's country entry processor will be working with the binary objects, and the type of the key will be string as before, but the type of the value will be binary object. That's it. So we fixed all the compilation issues. So right now, let's restart our application, and it has to be fully workable. All right, wonderful. You see, like this time we could fix this whole application, and right now it works as expected. So Donald Trump, that's what we updated before, and then with this logic, we checked who was the current prime minister of the Great Britain. That was Elizabeth II. Then we updated to the Boris Johnson using binary entry processor, and we use binary objects to update or read records on the server machines. That's how you can use key value APIs, and that's how you can use peer class loading to deliver classes to your server nodes right from the application. That's one of the most powerful features of Apache Ignite. And our server nodes stay agnostic to the state of the application. They just store the data, and they don't need to store any custom logic like POJOs or like your computations. That's what we wanted to do. Okay, really quick, I'm checking the question. Someone is asked the question. That's from Ken. I assume that the affinity key name country code has to be unique across the tables. What if there is more than one table with country code? No, in fact, this country code is unique. Yes, the country code is unique across all the tables, and actually that's the code of the country. Like what we name code in the country, it's unique, and that's your primary key. And we are just using the different name like country code in the city table, and that one is unique as well. But I mean, like when it comes to the city records, the uniqueness of a city record is defined by the compound key. You need to have the both ID of the city and country code. But the country code is always used to calculate a target node where a record of a city is to be located. And that's what we are doing here. All right, let's jump back to the other topic. The next one is distributed transactions. So here is with Ignite. You would use distributed transactions when you need to update 2 or more records atomically. And those records can be located in different tables, in different caches, and they can be placed and spread across several cluster nodes. It's up to you. And Ignite distributed transactions allow you to do all those changes atomically and consistently. So this second application that we have in here, what it does, this application, again, that's a simple Java application that connects to our 2 nodes cluster. It gets a reference to our city cache. So right now we're going to use cities, and then it tries to update 2 records stored there. In particular, we are going to access the record of New York and then the record of Los Angeles. And then inside of the transaction, we want to update the population of those cities. Here is, we just imagine that 10,000 people moved away from New York to Los Angeles. They decided to move to sunny California. And we want this change to be done atomically and consistently. That's why, as to do suggestion here, we need to complete this transaction, because right now, inside of this transaction block, repeatable, read pessimistic, we are just getting back these records, and we are doing nothing with them. So to update this, let's do the following. So first of all, I am saying that 10,000 people moved from New York, so we need to decrease the population of New York City, but at the same time, all those folks moved to Los Angeles. So we are increasing the population of that city respectively. Once you do this, you need to write back these 2 records using the same familiar caching APIs we used before. So we are using New York primary key, and we are placing back this New York record, and the same for the Los Angeles primary key. All right, that's the whole application. So, and what happens here, we will update it, and then we will read these records back after the transaction is committed to ensure that the population has been in fact modified. All right, let me start this application. All right, it works perfectly fine. So before we executed our transaction, that was the population of New York and Los Angeles. And after the transaction has been successfully committed, that's what we've got. And we were able to update these both records atomically. If to show you how the city key looks like, as I promised, so here is, as with create table command, the key has to be compound, it's complex key. And here is our project class, includes two fields as well, ID and country code. And country code, we are telling Ignite that that's our affinity key. So whenever you will be updating or accessing these records with key value APIs, Ignite will be using the value of the country code to find this record or to put this record on a valid node that stores the primary copy of the city. All right. Okay, and I see that there is another question from Ali. So the question is, can we pass parameters to entry processor, like passing the Boris Johnson value as param? Yes, Ali, that's a good remark. In fact, you can do this easily. If we check entry processor APIs, here is their contract says that you can pass as many arguments as you want. So generally, yes, you can go ahead and optimize this implementation, because right now it's not the generic, right? So what you can do, you can basically update it in a way that this parameter is passed in here and you're just reading it back. All right. That's all for transactions. So they just exist. I just wanted you to know how to use them. The API is pretty straightforward. There is no any rocket science. And the next example that is more advanced I wanted to show you guys is distributed custom tasks. With entry processors, we already kind of touch the surface a little bit. Entry processors can be think of as our distributed little computations that allow us accessing individual records and update those records accordingly. While with custom tasks, with custom Java tasks, we can create some random custom logic that can be executed or broadcasted to all your cluster nodes, or that can be executed on particular machines, depending on your logic. And you would use those that advanced logic if, let's say, you need to iterate through your whole table, you need to scan your table. Or if you need to, let's say, if to give you some business examples, let's say you need to calculate delivery routes for your packages. You're like DHL company, you're UPS, or you're United States Post Office. You need to kind of do all those calculations like in real time. And there is no way you can use SQL or key value APIs for that. You need to run some advanced logic on your server machines where the data resides. And with Ignite, it's all simple. Ignite provides so-called compute APIs. That's just an implementation of the MapReduce paradigm. You just create your task, you run this task, you schedule this task for the execution, the task executes on your server machines, and then if needed, those nodes will return you a result set that you can reduce and probably do something useful with it. So what do we need to do with our world database application? So what's our next task? Let's refer to this template. So again, so here is this template. We are connecting to the cluster. That's an application. And then we are calculating average country population of a particular country. So here is we are calculating average population for Brazil and Russia. So what happens inside? This method is already implemented for us. So here is we are, as I see, we are getting access to the affinity interface of Apache Ignite for the country. And with this affinity interface, we can ask Ignite to return us, let's say, what's the partition number for the country code, for this specific country code. Why do we need this? Because as you remember, all the countries, all the cities of a specific country are stored on the same machine. But in fact, if to be more precise, all the cities are stored inside of a specific partition, and that partition is located on one of the cluster machines. And affinity key is used to kind of to do this translation to the partition, and then from the partition to a specific cluster node. And here is, with this logic, we are saying, all right, that's my partition number, and then I want to run this computation on the cluster node. I want to run this computation on the cluster node that stores the primary copy of this partition. Because I know that all the cities of this country are stored inside of this partition. That's just what's given to us by a contract. That's how Ignite works. And then once this logic gets executed, it returns us some result. And inside of this result array, I will have the country, I will have the average population and the total number of the cities in that country. And now if we look inside of this average population task, what happens here? It implements Ignite callable interface. Here is we are passing this parameter, partition number, I want to scan through, and the country code. And then inside I'm creating, again, that's the server node. I don't have POJOs for the city. I'm going to use binary objects as it was before. Here is I'm using the binary object abstraction for both city key and the city POJO. And then I'm running this scan query. I have this filter, and that filter is left unfinished. We have to finish its implementation a little bit later. But then I'm saying that that scan query will be local over the local data. And for every record return for this scan query, I'm going to calculate total population, cities count, and then I'm just going to return this average population back to the application. All right. So if I execute this logic right now, first of all, my server nodes don't have this logic in the class path. Again, it will be the bytecode of this class will be transferred to the server nodes automatically from the application. And here is what's happened. Actually, the logic calculated something. You need to believe to the response. That's the average population of the cities in Brazil. That's the average population of the cities in Russia. And that's the total number. But we know that there is a to-do, and we have to finish this logic. Let me do the following. I will remember this. Response so that we can compare. And what happens here, we need, the instruction says that we need to ensure that the scan query calculates the data only for the records that belong to my country code. Because what's the problem? Because inside of this partition, yes, I will be storing all the records of Brazil, for instance, but also in the same partition, I can store records of the cities who belong, let's say, to the United States or to Canada, etc. And I don't want to count them. And it's easy to fix. So let's do the following. I have object, I have key object, and I want to check that the field, which is country code, the value of the country code of my key is equals to the country code that was passed into these calculations. So yes, if let's say with the first execution, I'm calculating all the cities of Brazil, if the record that is stored in this partition is in Brazil, then I will account it while I'll calculate the total population. Otherwise, I will skip this record. Okay, let's restart this application. The logic was updated. It will be reloaded for the server nodes. All right, and right now we have this response. Let's compare it to the previous one. Yep, looks like that in the same partition, the partition that stores the records of Brazil, we have cities of some other country. That's why when we finished implementation of our scan query filter, right now that's the valid result. That's the average population of Brazil, and that's how many cities we have in Brazil in this database. But as for the Russia, let's say, turns out that the cities of Russia were the only cities that were located in the partition that stored those cities, the Russian cities, and there were no any other cities in that partition. That's what we've done. All right. Okay, that's the compute task. So basically, with compute tasks, you can create your random custom Java logic compute tasks that can be executed on your server machines, and then in a fast manner, you can iterate through your data sets. You can scan through data sets. You can run local SQL queries. You can do local key value requests, whatever you want to do. And here is, I was running this compute task on one of the cluster machines, but also you can broadcast your tasks if, let's say, you want to just use all the CPUs of your cluster for some other compute-intensive calculations. All right, and going in, and now we are heading to the finish line. And let me show you what we can do if we are willing to subscribe to data changes. Here is we can use continuous queries. What continuous queries are designed for? Actually, your application can subscribe to any data change. That continuous query will be registered with your server nodes of your cluster. And then whenever records get updated, you will be notified. And every application requires to start a unique continuous query so that depending on the needs of the application, you can listen to the updates that are coming. And here is we have the very last source code template that was prepared for us. And as before, we need to finish it. Again, we are connecting here using this this client mode. And right after that, I'm subscribing for data updates. I'm creating this continuous query. I'm setting this local listener. So the local listener is the interface that will, where my application will be receiving updates from the server. So that's like this listener will be executed and running and triggered on my application end. But also I'm registering the remote filter. And this remote filter will be registered on the server nodes. And it allows us to decide which updates we'd like to be notified about. For instance, I don't want to be notified about every change with my data. And that's what we are going to do next. So once you define your continuous query in your application, then you just need to execute this query. And again, here is I'm using this with keep binary approach because inside of this remote filter, I'm going to use binary objects. Again, I don't want to put and I don't want to keep project classes of my data model, project classes of my model objects on the server nodes. That's why I'm using binary objects. But at the same time, when I will be receiving all those updates to the on the application end, I will be able to deserialize all this data to the project classes because these project classes are by definition available to the application. Okay, so once I register this continuous queries, I will go ahead and update a couple of records. I will actually decrease the population of Los Angeles again and using SQL queries. So let's do this. I run this query. Okay, it was registered continuous query, and actually that was the very first notification we received inside of our local listener. So with that SQL query, in fact, we have updated 2 Los Angeleses. So in fact, we have Los Angeles in California, United States, and we have Los Angeles in Chile, as far as I understand. So like the same cities, the same name. And we updated the population. So right now, like what this application, what this source code template suggests us doing is to kind of to update this filter in such a way that we are notified only if the population gets updated. So why so that? For instance, right now, let me go to the control center. If I want to, if I update the name of Los Angeles, let's say LA, right? I run this query. Then I will receive this notification, right? That's a valid response because my filter returns and reports on every data update that happens in the cluster. But what if I want to receive updates only or only if the population changes? And we can do this easily. Okay, so what we need to do? We need to take we need to ensure that the population record, the population field has been changed. In fact, we are taking the old value, field population, and equals get value field population, and that will be not equal, right? So generally what it says, the filter will return updates only if the population record has been changed. And we are just comparing the value of the record, like the old value of the record and the new value of this record. And right now, all I need to do is to restart my application. And again, for these filters, Ignite also leverages from the peer class loading feature. You see that I have updated the implementation of this remote filter, and this remote filter is executed on the server nodes, but I'm not assembling any jar files. I am not restarting my server nodes. Generally, when this continuous query gets registered with the servers once again, the server nodes reload the byte, the new class implementation of this filter, and that happens in background. You just update your logic. You don't need to touch your cluster. All right, it was restarted. So, and right now I expect to receive updates only for the population field. So let me do this exercise. Let me update the name again. Los Angeles, I updated. All right, it was updated, and I'm not seeing any update. That's a different record. That's the different ID, as you see. That's the Los Angeles of Chile. But let's say if I update population, I will receive notification. All right, that's what I've done. So generally, right now we created a continuous query, and that continuous query updates our application only if there is a change with the population field. That's what we wanted to do. And this remote filter can always be updated in runtime. You can reload it, and you don't need to restart your server nodes. My server nodes, as before, they're just running, and they're just processing our requests, SQL queries, continuous queries, etc. That's my database. All right, folks, and we have exactly 5 minutes left, and that will be enough to demonstrate our last feature, like durability with Ignite native persistence. As you remember, all the time this persistence was enabled for our cluster. It's done this way. I'm just in my storage configuration, I'm saying that persistence needs to be enabled. What it gives to us, first of all, it allows us to keep much more data on disk than it can fit in memory. With this Vault database example, my memory space was enough to keep everything both in memory tier and on disk tier. But if, let's say, you're storing much more data and you don't have enough RAM, then you don't need to kind of stress out your memory. You will keep all the data on disk, and then as much as you can in memory. And Ignite will read all the missing in memory records from disk for you. And also, as long as Ignite can read records from disk automatically, on cluster restarts, you don't need to warm up your cluster. Once the cluster is restarted, once the nodes are interconnected, the cluster becomes operational. And our applications can read all the data from it. And Ignite will serve all those records from disk, warming up memory in background. So let's do this exercise right now. What I'm doing, I am just shutting down my cluster abruptly. Let's assume that it just crashed for some reason. A power outage has happened. If I'm going back to the control center, yep, I can see that the cluster is down. It will kind of wreck a little bit soon. Yep, the cluster is disconnected. Now I'm restarting this cluster. All right. Continuous queries. Yep. Continuous queries. I need to stop this continuous query for now. I can restart it later. Because I was trying to find, yes, I don't remember the reason of that mistake, that exception, but yeah, it can be easily fixed. You can just restart that continuous query. All right, the cluster is restarted. The nodes are up and running. Okay, the cluster is active. Let me go to the dashboard and check what happens here. So these metrics should be updated right now because I don't think that they're correct. In fact, I should have, yep, I have all the records in memory, but I don't have anything. I have all the records on this, but I have nothing in memory. Most likely that's, just, something that was some default size. But the data is on disk, right? And if I keep running these queries, I'm getting this result back. So the cluster is operational, right? If I restart my continuous query example, it will work perfectly fine. So I don't need to reload any data. I'm not warming up my memory. The data is served from disk, but the memory is being warmed up in background as long as I am requesting and querying my cluster. Okay, so that's it. All right, so having said that, as a summary, so throughout this conversation, what you've learned, my goal was to demonstrate you all the essential capabilities of Ignite through the coding examples. And most importantly, as you see, especially in the beginning, we were fixing a lot of the exceptions. We were fixing a lot of the mistakes, and we were finishing some of the implementation of the logic. Most of those exceptions and most of those implementation aspects, you would hit them, you would come across them when you're writing your applications. And just keep that in mind. If you want to repeat, if you want to do this yourself, just go ahead, download this GitHub project, and you can build it. You can experiment it with home. Also, I was using this GridGain control center. That's a monitoring tool that is available for both Apache Ignite and GridGain clusters monitoring and management. So right now, it's available as a hosted solution, but in a couple of weeks, you will be able to download and install it using binary packages or Docker images on your premises. And if you would have any questions, let's say related to this demo project or anything else, you can always reach me out over Twitter. That's my Twitter handle, or you can find me on LinkedIn. And the final thing to mention is that we have just started. We are going to announce soon our virtual Apache Ignite meetup. So that's the place where we are bringing together not only Apache Ignite development community, but also those who use Apache Ignite actively in productions. And that would be the place where we will meet together as a whole broad community to discuss the pros and cons of Ignite, to discuss best practices, to see how Ignite production architectures look like. So if you're interested in that, that's the link, that's this QR code. Join us. Soon we are going to announce the very first talks. And if you already have any Ignite story to share, reach us out on the community dev list. All right, folks, thanks for finding the time and joining this webinar today. And let me see if you have any other questions.
Is there any preferred Java distribution or version that's recommended for Ignite?
You mean like Java virtual machine? Or yeah, so again, for Ignite it doesn't matter. So by default we use, if I'm not mistaken, historically before Oracle has changed the licensing terms, Ignite community used Oracle GDK for testing, for development, etc. Right now we are switching, let's say, back to the OpenGDK and other distributions. We also, when it comes to GridGain, we collaborate closely with Azul. We use GridGain, Apache Ignite, and Azul Zine virtual machine for low latency use cases, because Azul Zine goes with their proprietary C4 garbage collector, which is postless. It kind of handles large Java heaps for high throughput applications more elegantly. And but overall, like also we know that Ignite is being used on IBM GDK if you're running Ignite, or GridGain on mainframes, etc. But generically, I would say that for most of the use cases, that's OpenGDK or Oracle GDK, and then you can select between Azul Zine, Azul, Zulu, or like IBM, depending on your preferences. For us, it really doesn't matter.
Great. There's one question from Ali. He's asking about, are continuous queries meant to be consumed by microservices or also by end users?
Yeah, that's a good question. I would say that that's an API for your applications. Let it be a microservice, or let it be a monolithic application. So let's say that if by any means your application wants to get those updates, then you can get those updates using that API. As for the end users, you might present like the results of those continuous queries. Let's say you can have some mobile application or some front-end application, like some web application, that shows some notifications when an update happens. But that notification will be displayed only when internally your logic, your microservice, receives that update through the continuous query API. But then, yes, depending on your logic, if it's a mobile application, if it's like front-end application, web application, you will display this kind of, you will handle it somehow. If the user needs to see it, you will probably show some notification or hint or whatever, etc. If to give you like a real world example, for instance, there is a company, RingCentral, they develop, I know that they use continuous queries heavily. They develop kind of like video conferencing and voice conferencing software. So basically, it's like this one, like Zoom or GoToMeeting, when you just can create some different meeting rooms. You just get together there, and they use continuous queries to update on the new participants. Like, let's say that you have started and there were only 2 participants in the meeting, but then someone else joined it, and they kind of receive all those updates through continuous queries. And then my instance of the applications of this video conferencing application will receive this update through continuous query, and then it will update the attendees, the participants list, like the UI. That's how it works for their case. Some other customers may use continuous queries to trigger some calculations. Let's say some important event happened, you updated, let's say you are kind of dealing with, let's say, packages delivery, your UPS or United States Post Office. You delivered a package to the door of your customer, and the delivery guy just, responded in the application that, all right, the package has been dropped near the door. And then this kind of your backend system, your enterprise system, through continuous queries can get this update, and then can send the notification, email notification or push notification to the mobile phone of the guy this package was delivered to. So that's how you can do this, just to give you better understanding of the real use cases.
Awesome. I think that is the last question. So that brings us to the end of the webinar. Audience, as I mentioned, we have recorded today's session, and I'll be emailing you a link to the recording and to the slides. Okay. Thanks, Denis. Thanks, everyone. Have a good day.
Yeah, thanks everybody.
Bye.
Yeah, enjoy the rest of your day.